Good morning, students. Hope all of you are doing fine. So this is the second second class on the potential and capacitance chapter of your NCERT. The previous class we devoted some time on discussing the concepts of two important parameters. One was potential difference and second it was potential. Before proceeding further, I would like to recapitulate what we discussed in the last class. So these are the important points that we have discussed. The first important thing, potential difference between 2 points, which we denote as delta V, and suppose the 2 points are A and B, so that potential difference we write as VB minus VA, and that we have defined as negative of work done by electrostatic forces or electric field, or positive of work done by external agent in bringing unit positive charge from one point to the other. If I have one point here, I wish to find potential difference between these 2 points, then I need to simply bring 1 coulomb of charge, unit positive charge, from one point to the other point. While doing so, whatever work is done by me, that is equal to potential difference. Or while doing so, whatever is the work done by electric field or electrostatic field, its negative will be equal to potential difference. So mathematically we can write it as negative integral of E dot dr. I have explained last class. This is actually work done in bringing unit positive charge from first point to the second point, initial to final. See, this is the potential difference. So always you should remember like this is final minus initial. So here you have to go from initial point to the final point, and negative of E dot dr. That was the definition for potential difference. Extending this particular idea, you see this expression, I can write, if I cross multiply this charge I can bring over here. So minus WEL, which will be equal to plus W external, and that Q I will multiply to delta V. So this becomes Q times delta V. And as I have written, very important, remember this particular relation. What does that mean? That instead of 1 coulomb, if I bring charge Q from one point to the other point, then in bringing this charge Q from one point to the other, I have to do some work. That work is W external. So that work will be equal to the product of this charge Q and the potential difference delta V between these 2 points. So always remember this. And I have explained last class that the external work done is always negative of electrical work done. You can see the reasons over there. So W external is equal to minus W electrical, that is equal to charge multiplied by potential difference. Because this is so very important, I want to stress on this particular formula. So I am writing in words also, charge times potential difference. PD I am denoting it for potential difference. Having understood this, then we took a convention. What convention? That potential due to some charge configuration V at infinite separation, that we have taken as 0. If this convention is valid, then we can define potential at a point. Suppose there be a point whose position vector is r. I should write here VR vector in general. Then potential at that point is defined as negative of work done by electrical forces or electrical fields, or positive of the work done by external agent in bringing unit positive charge from the reference. What is our reference? Our reference is infinity to the given point r. So infinity to r, if you bring unit positive charge, you have to do some work. That work, external work, is equal to potential at that particular point. Then we have discussed potential due to point charge. Using these expressions, we have derived that if there be a single point charge at some point, then due to this charge at a distance r, the potential is given by this formula 1 by 4 pi epsilon naught q by r. And we have seen the unit for potential, the SI unit for potential as well as potential difference. If you remember students, it's joule per coulomb because it is work by charge, that we also call as volt. So these are the things that we had discussed in the last class, students. Today we would need this particular equation time and again. So please remember this: W is equal to Q into delta V. External work is equal to charge into potential difference. I would suggest all of you to write these formulae as a summary in your note, then proceed further for the next topics. Next topic that I would like to discuss today, students, after potential and potential difference, we would switch over to potential energy and likewise potential energy difference. This we would denote by U, and the difference in potential energy we would denote by delta U. Now here is the definition for potential energy for a given system of charges. Suppose you have some set of charges Q1, Q2, Q3, Q4 and so on, n charges are there, and they have some separation, intercharge separation as shown. So this is a system of charges. We wish to find what is their electrostatic potential energy U. Then here is the definition for them. What we need to do, one by one we would bring these charges from infinity to their given location. Suppose this is origin, Q1 is at position R1, Q2 is at position R2 with respect to this origin. First of all, what you will do, assume that nothing is there. We would bring charge Q1 from infinity to this point. Then we would bring charge Q2 from infinite separation to this location. Then we would bring charge Q3, then Q4, and likewise we would bring all the charges one by one. In doing so, whatever is the external work done by me or by the external agent, that is equal to potential energy of this particular configuration. This definition will be true only when we assume one convention that potential energy for any charge configuration at infinite separation is taken to be 0. So here is the definition. Again, either you define in terms of external work or you define in terms of electrical work. Only difference will be that of sign. So potential energy for a system of charges may be defined as negative of work done by electrical forces or electrostatic forces in assembling the charges from infinity or infinite separation to their given positions or configurations. Or you can also write, it may be defined as the external work done. When you write external work, it has to be positive. Rest part will be same. The external work done in assembling the charges from infinite separation to their given separation. So this is the definition for potential energy. This idea, along with this idea which I discussed previously, that any work done in bringing a charge Q from one point to the other, from say point 1 to 2, if you bring charge Q, then this work done is given by which formula, students? The product of that charge into potential difference between these 2 points, which I can write as V2 minus V1. With these ideas, we would like to discuss some of the cases for potential energy. Let's see one by one. Let's see first how to calculate the potential energy for a pair of charges. If we have 2 charges Q1 and Q2 separated by some distance R12, then as per the method which I discussed just now, first I will bring charge Q1 from infinity to this point. For that I need to do some work that I write as W1. So W1 is the work done by external agent, in bringing charge Q1 from infinity to, I name this point as A, this point as B, to infinity to A. Now this work done W1 remember Q2 is not present here. First I am bringing Q1, then I will bring a Q2. So when I bring a Q1, before it is brought, there was no charge over here. So there is no electric field. So I will not feel any force to pull it. If there be some charge configuration, then to bring some charge, this charge may be attracted or repelled. I will exert some force. Some force has to be exerted. Suppose we have a positive charge here and I am bringing a positive charge towards it. Then there is a repulsion between them. So I have to exert some force. So I will do some work. But if there is no charge, no electric field, then to bring a charge, I will not do any work against electrical forces because there are no electrical forces. That's why this answer will be 0. Please convince yourself that W1 must be 0. Now Q1 has been brought. Since charge Q1 is now at its place, in region around itself, it will create some potential. It will create some electric field. So next time when we bring charge Q2, that Q2 will suffer some attraction or repulsion depending upon their signs. So that means that Q2 will experience some electrostatic force. Against that electrostatic force, you have to apply external force. So likewise W2 you will write, let W2 be the work done by external agent in bringing charge Q2 from where to where? From infinity to its location that we write as B. Now, how will you find W2? W2, I will use this particular formula. The work done in bringing charge Q2 from one point to the other will be given by the formula that charge multiplied by potential difference. Now, which is the initial point? We are bringing from infinity to B, initial to final. So, when you write potential difference, it should be VB minus V infinity. Now I have already talked about the convention, students, that potential due to some charge configuration at infinite separation is taken as 0. So this becomes how much? This becomes Q2 multiplied by potential at B. At B now there is a potential. Earlier there was no potential at A. That's why this work was 0. At B there is some potential that we write as VB. That potential is due to whom? Due to Q1. So what is the expression for potential due to a point charge? That value you have to put here. If you remember, that value is 1 upon 4 pi epsilon naught times this charge, that is Q1, by this separation, that is R12. So this is our W1, that is our W2. Therefore we find the next external work, net external work or net work done by external agent, W, that will write as W external. This will be equal to W1 plus W2. But since W1 is equal to 0, that's why W1 plus W2 we can write directly as this sum, that is 1 upon 4 pi epsilon naught times Q1 into Q2 upon R12. And by definition, this external work done to assemble the charges from infinite separation to their given separation is called as potential energy. So therefore by definition, potential energy is nothing but W external, and this becomes equal to how much? 1 upon 4 pi epsilon naught times Q1 Q2 upon R12. So that is the expression for potential energy for a pair of charges. Now instead of two charges, if we have suppose more charges, what would happen? Let's see that also. Suppose now we have a charge configuration like so, wherein we have three charges Q1, Q2 and Q3 separated by some distances R12, R23 and R31. We have to find potential energy for these three charges. First what we will do, step 1 is what? So step 1 will be charge Q1 will be brought from infinity to A. I'll call this point as A, this point as B, this point as C. You should write the language yourself. Step 1 is Q1 will be brought from infinity to its given location. As I have explained in the previous case, the external work done in this case will be 0, because we assume that prior to bringing Q1 there were no other charges to create electric field. Now what will be our step 2? Step 2 will be to bring charge Q2 from infinity to its position, that is B. Since we have already brought charge Q1, at B there is already some potential. That potential is due to whom? That is due to Q1. This potential Q3 we have not yet brought. You should understand that. So VB will be how much? 1 upon 4 pi epsilon naught times this charge, that is Q1, upon this distance, that is R12. Since there is some potential at point B, now so if we bring Q2 from infinity to this point, we need to do some work. The external work done by the external agent in bringing charge Q2 from infinity to this point, will use this formula, will be given by the product of that charge into potential difference. Now potential at final point, that is B, minus potential initially, that is at infinity. Now we had discussed, students, potential at infinity will be how much? 0. So what is left behind? Q2 times VB. So VB is this much. So if you multiply Q2, how much will you get? 1 upon 4 pi epsilon naught Q1 into Q2 upon R12. So step 1 is done. Step 2. Now we have step 3. What is step 3? It will be to bring charge Q3 from infinity to its location, that is point C. So before finding work to do so, we should know what are the potentials at these 2 points. At infinity we know the potential to be 0. At C, what is the potential? So potential at C is due to whom? First you should ask that. At C, the potential is due to only Q1 or only Q2 or both. What do you think? Since already Q1 and Q2 have been brought, both the charges are present, therefore both of them will create an electric field and hence some potential at this point. So remember, potential at C is due to both of them. So you can use the concept of principle of superposition. That will be total potential is 1 by 4 pi epsilon naught, which I can take common. Due to first charge it will be Q1 upon this distance R31, and due to the second charge it will be Q2 divided by this distance, that we write as R23. And now we are ready to find the work done in bringing charge Q3 from infinity to this point, that is C. So W3 as per this formula should be that charge which we are bringing, that is Q3 multiplied by potential difference. So potential at final point, that is C, minus potential at initial point, that is infinity. And we know potential at infinity is to be taken as 0. So this expression becomes how much? This becomes Q3 multiplied by Vc. So in this expression I have to multiply Q3. So 1 by 4 pi epsilon naught multiply Q3. So Q3 Q1 upon R31, and plus here also we multiply Q3. So Q2 times Q3 upon R23. So this is our W1. This is our W2 and this is our W3. You can guess what should be our next step. Our next step is to find, so we have assembled the charges. Now we need to find the total work done. So the total work done by external agent in bringing or in assembling the charges is given as W external is equal to W1 plus W2 plus W3. Now if you add them, what should we get? So let's see, W1 is 0. So W2 plus W3. W2 and W3 we can take 1 by 4 pi epsilon naught common. So 3 terms will be there, Q1 Q2 by R12. Second term Q2 Q3 by R23, and third term Q3 Q1 by R31. By definition, the potential energy for these three charges is nothing but W external, which is nothing but this much. So that is the expression for potential energy due to three charges separated by some separation. So we saw for two charges the formula was 1 by 4 pi epsilon naught, product of charges by separation between them. If you see, it's easy to remember this particular formula. What we have to do, when we have three charges, you choose pairs. Pair-wise you write the formula for potential energy and then add them up. For example, this is one pair. Before this we have done potential energy for a pair of charges is given by the formula 1 by 4 pi epsilon naught, product of charges by separation between them. So for this pair 1 by 4 pi epsilon naught Q1 Q2 by this distance, that is first term. For this pair you can see 1 by 4 pi epsilon naught Q2 times Q3 divided by R23, that is this one, and likewise for this pair we have got this answer. If we have understood this, then instead of 3, if we have 4 charges, can you guess what should be the expression for potential energy due to these 4 charges? Suppose I give you a situation like so. Q1 is here, Q2 is here, Q3 is here, and Q4 is here. And these separations are suppose given to you. This is R12. Can you tell me how many terms will be there? For 2 charges we wrote 1 term, for 3 charges we wrote 3 terms, for 4 charges, point charges, can you think of how many terms should be there? Will it be 4? Are you thinking it's 4? Let's check out whether it's correct or not. If these 4 pairs have come to your mind, you should also add this one and this one. That is also one pair, that is also one pair. So out of 4 you have to choose 2. So there are 6 possible ways of doing so. 1, 2, 3, 4. 4 pairs are like this. This is also one pair, 5th pair, and this one is the 6th pair. So if those separations are given to you, suppose this separation is A, this one is B, this one is C, this one is D, this distance is E, and this distance is F. Then what should be the expression for potential energy for this system? Potential energy for this system will be 1 upon 4 pi epsilon naught times Q1 Q2 by that distance A plus. Now I think you can easily understand. So I'm just writing, you can follow it from there. And the 2 diagonal parts, I think now you can likewise decide in other cases of charge configurations given. All these we have discussed for discrete charge configurations. We shall also see later on how to solve questions pertaining to continuous charge distributions. Now before proceeding, let me summarize what we have discussed so far. Points 1 and 2 in the beginning of the class I have already discussed. Anyway, for your reference, potential difference and potential. If it is potential difference minus integration E dot dr from one point, first point, initial point to the final point, and if you are bringing from infinity, then it becomes potential at a point. So here the integral is from infinity to r. After that we have discussed about potential energy. Potential energy is defined as negative of work done by electrical forces or positive of work done by external agent in bringing the charges from infinity to their given configuration, in assembling the charges from infinity to given configuration. We have seen for a pair of charge, for 3 charges, 3-point charges, 4-point charges, the expression for U. Then we also discussed that if a charge Q is brought from one point to the other, then the external work done is equal to the product of this charge into potential difference between these 2 points, like so. Now in this third point, we have discussed about potential energy. Now suppose there are some charges and I take one charge and I change its position to some other point. Then do you think its potential energy will change? Of course, because the separation is changing. In doing so, I have to do some work. So change in potential energy will then be defined as we have discussed, for potential energy from infinity to given configuration, here from initial configuration to final configuration. If you are changing the positions or configuration of charges, their potential energy will change. Then we define a term called as change in potential energy, which may be defined as the negative of work done by electrical forces or positive of work done by the external agent in assembling the charges from their initial configuration to final configuration. If the initial configuration is at infinity, that potential energy becomes 0. The same thing turns out to be the potential energy at a given separation. With these in mind, let us see some questions. This is an example from your NCERT. You can, for a reference, see example 2.2 of your textbook. There are 2-point charges, 3 into 10 to the power minus 8 coulomb minus 2 into 10 to the power minus 8 coulomb, separated by a distance of 15 centimeter. Question it is asked, at what points on the line joining these two charges the electric potential is 0. See, this is positively charged, this is negatively charged. It will have positive potential, it will have negative potential. So we choose some point on this line at distance x. Now this x should be towards O or towards near to O or A. That will depend upon their magnitudes. The magnitude is more here, so it should be away from the 3 times 10 to the power minus 8 coulomb charge. It should be near to the charge at A. If this be x, the other separation will be 15 minus x, where these lengths are in centimeter. Let this point be something P. So the total potential at P has to be how much? 0. Now potential at P due to this charge will be how much? 1 by 4 pi epsilon naught. This I will write as Q1, this I will write as Q2. So I can take this common. We will have Q1 by this distance will be x plus other charge is Q2 upon that distance will be 15 minus x. This total is how much? 0. Now what is the value of Q1? Q1 you will put as 3 into 10 to the power minus 8 by x plus Q2 will be minus 2 into, so this becomes minus 2 times 10 to the power minus 8 upon 15 minus x is equal to 0. This equation can be solved easily, students, so I will not solve it. Solving this, you will get x is equal to 9 centimeter. Now you can see this is 15, this is 9 centimeter, x is 9 centimeter, so the remaining part is 6 centimeter. So at this particular point, distant 9 centimeter from charge Q1, the potential will be 0. Wait a minute, but this is not the complete answer. Is there any other possibility of the location of such a point where potential is 0? Can it be in this region to the left of O or to the right of A? To the left of A, to the left of O, any point if you choose, that point will be closer to that charge which has a greater magnitude. So it will always dominate. So complete cancellation is never possible, plus and minus. But if you switch over to this particular region, so this point is close to this charge, but its magnitude is less. And this is far from this charge whose magnitude is more. So there can be some sort of balancing effect between them. So one more possibility is there. That point I will write as Q. So this is first part which I have done. For other part, Let x be the distance of this point Q from O. So how will our equations modify? 1 by 4 pi epsilon naught Q1 upon this distance is x, no problem. Q2 upon this distance. Now this distance will be this total minus this, that is x minus 15. So instead of 15 minus x, it becomes x minus 15. And the rest you can solve it yourself. Q1 and Q2, put the values and solve. You will get the answer x is equal to 45 centimeter. So there are two answers for this. In between the 2 points at point P, which was at a distance of 9 centimeter, and to the right of A, also you will get some answer that is at a distance of 45 centimeter. Okay, let's see a question. This is from H.C. Verma. This question gives you an idea about how to obtain potential if electric field in a region is given. So here E vector is given A by x cube I cap. This is the magnitude and this is the direction. A is some constant. If we are given electric field in a region, question is this, that you have to write an expression for electrostatic potential in this region, assuming the potential at infinity to be 0. This is our convention. Potential at infinity we take as 0. So I have discussed, students, that potential at some position, let that position have position vector r vector, is given as minus integration of E dot dr from infinity to given position. Now E vector is known to us, but if you see carefully, E vector is along x-axis. You should understand, students, dr vector. In one dimension we can take dr vector as dx or dy or dz. I will elaborate this point a bit, please listen carefully. Dr vector in one dimension can be written as dx I cap, or it can be written as dy j cap, or it can be written as dz k cap. If there is only one dimension, so this is the value dx along x-axis, dy along y-axis, dz along z-axis, depending upon which axis you are considering. But if it is a general in two dimensions, like so, this is y-axis, sorry, this is x-axis, this is y-axis. If we have displacement dr, then it can be resolved into two components, one along x and one along y. Then dr vector in that case can be written as this vector plus this vector. So there it becomes dx I cap plus dy j cap. This will not be there. Likewise, in three dimensions you should have this. So remember, a differential displacement that we write as dr vector in one dimension can be written as dx I cap if it is x-axis, and likewise for other axis. In two dimensions it should be written as dx I cap plus dy j cap, and in three dimensions dx I cap, dy j cap and dz k cap. So that we shall do over here also. E vector value is how much? A upon x cube times I cap. Then dot product. Dr vector will write how much, students? dx I cap plus dy j cap and dz k cap. Now when you take dot products with this, I dot I, you know, it is 1, I dot j is 0 and I dot k is 0. So these two terms on taking dot products will give the result 0. So what is left behind? A upon x cube times dx, and I cap dot I cap will become 1. So that will be the integration, and the limits are from infinity to r, and I have forgotten to put the negative sign, so you have to put negative sign. Now instead of r I will write, since it is only along x-axis, this integral, the variable is only x, so I will write it as x. This integration can be easily solved. So integration dx by x cube, so that will become, actually this limit, if from infinity to, it should be x comma y comma z, because we don't have y and z, so no need to write that. It will be like so. So minus a will come out of the integration. Now dx by a cube will become x to the power, dx by x cube, x to the power minus 3 plus 1 by this much, and the limits will be from infinity to x. So this becomes how much? So minus and minus becomes plus, a 2 will be there. This is 1 by x square. So from infinity to x, first we'll put x and then we'll put infinity. So this tends to 0, and therefore the answer will be a upon twice of x square. This should be the expression for electrostatic potential if the electric field is given in this particular fashion. Now see, this electric field formula can be anything. Always understand the fact, students, that if electric field in a region be given, whatsoever be the expression, and you are asked to find the potential, it is this formula which you have to use. So I will stop here, students. Please try to do the questions given in the assignment. Next class I will come up with some of the questions on potential, potential difference, potential energy, electric field and potential relation, and so on. I thank you, wish you all the very best, read well.